This is Bob, an avid graph comparer. His job is to compare Raman Shift's graph in order to classify pen into their respective brands. Different types and brands of pen is believed to have different Raman outputs. What Bob does is he tries to find a graph that matches with his goal. A graph that looks different means the pen do not belong to that brand, while a graph that looks similar means there is a high probability the pen belongs to the brand and type. But what if there's too many graphs? Clearly, Bob needs some help. We have a solution! Our novel system will quickly and accurately classify these pens from Raman Shift data for Bob. Instead of looking at tons of graphs, our system will return the top 3 candidates for Bob. Our system guarantees a match within the top 3 returned graphs 94.5% of the time. Now let's see how our system works. We first obtain our pen data from Raman machines. Although these machines are quite accurate, there are still measurement errors that could occur. For instance, these 2 graphs came from the same sample, but the location of the peaks are different. Therefore, in order to solve this problem, we group the data into what we would like to call them buckets. So what would happen to the value of the data when we group them into buckets? The value that is returned would become the average among each individual buckets. After we have grouped our data into buckets, our system deals with meaningless outliers that comes from cosmic rays during data collection by setting them to 0. With the data preparation complete, we are ready to move on to the heart of our project, the classification model. The classification model we choose for our system is the support vector machine, which is also known as an SVM. In order to understand SVM, we first look at a simple linear classifier. A linear classifier is a way in which we separate 2 groups of data from each other by using a straight line. However, there are infinitely many lines that could divide the data into 2 groups. What SVM does is it finds the line with the most margin, meaning the distance from the closest data point of each group to the line is maximized. Doing this ensures correct classification even for ambiguous data. During testing, an unknown point will be put into our model and we will classify whether the point belongs to which group based on the location where the point resides on. For our system, we expand this simple linear classifier or simple linear SVM to more dimensions. Specifically, each bucket represents a dimension in the classification space. Each Raman Shift sample represents a point in that particular space. Now, instead of finding a line, the SVM will find a hyperplane that best separates these points. With our model, we have succeeded at an accuracy of 80%. However, we have discovered that for practical purposes, returning the top 3 results would be more beneficial to the user. What top 3 means is that the pen sample is guaranteed to be in these top 3 results. This approach results in a more accurate system, specifically improving the accuracy to 94%.
I found a love for me. Darling, just dive right in, follow my lead. Well, I found a girl, beautiful and sweet. Well, I never knew you were the someone waiting for me. 'Cause we were just kids when we fell in love, not knowing what it was. I will not give you up this time. But darling, just kiss me slow. Your heart is over.